Using traditional logic, it might look something like this, where you have a car in front of you that's far away or close, and there's some value in between where it switches. The car being close can either be yes or no, 0 or 1, and the brakes can either be on or off, again 0 or 1. So in this situation, the car is far away, so it's not close, and the brakes are off as a result of this. Now in this situation, the car is now close, represented by 1, and the brakes are now represented by 1 as on. Now this might be a problem because the car is now applied the brakes with full pressure, and you're going to slow down very quickly, even though the car in front of you might not be approaching you very quickly, it might not be moving at all. So instead of doing something like that, let's consider using fuzzy logic. So this is your situation, and now, going from close to far, you have this gradient. And you can say, is the car close? Well, it's anywhere between 0 and 1, this range. And the same thing with the brakes, you can apply pressure between 0 and 1. So in this situation, is the car close? Well, 0.2. It's not very close. And as a result, the brakes, we're only going to put slight pressure on.
Essentially, it uses a control loop feedback to ensure the output wanted is what you will get. Simply, you put a setting in the controller and it will keep the output constant based on feedback from some input, typically some kind of sensor.
Satellites play a vital role in communication, navigation, and Earth observation. To perform these tasks, they rely on the Attitude Control Determination System, or ADCS, which ensures they maintain the correct orientation in space. This involves controlling 3 axes pitch, yaw, and roll, critical for pointing antennas, solar panels, or cameras in the right direction. The ADCS uses real-time feedback to stabilize the satellite. Sensors measure orientation and angular velocity, while actuators adjust the position. The control logic behind these adjustments include methods like PID control and fuzzy logic, each with unique strengths. PID control, short for proportional integral derivative, operates by calculating precise corrections based on error values. It's like steering a car to stay in your lane. Fuzzy logic, however, is more adaptive. It handles uncertainties by applying a rule-based approach, similar to how humans make decisions in changing conditions. By combining these methods, the ADCS achieves both stability and flexibility in managing the satellite's orientation. Space environments are unpredictable. Forces like solar radiation pressure, atmospheric drag, and gravity gradients constantly push the satellite off course. The ADCS combats these disturbances using actuators such as brushless DC motors or BLDC motors. These motors generate torque by rapidly spinning rotors, allowing fine adjustments to the satellite attitude while consuming minimal power. This hybrid control system, combining the precision of PID and the adaptability of fuzzy logic, enables satellite to operate efficiently in complex conditions. It's a breakthrough in satellite engineering, ensuring reliable performance for diverse missions across our ever-expanding ventures in space.
Okay, so now, building on the literature review, let's now look at the block diagrams of fuzzy controllers. The Fuzzy-Pid controller integrates fuzzy logic with a proportional derivative controller to manage errors and their rates of change, improving stability and reducing overshoot during satellite maneuvers. The fuzzy logic processes the error and its derivatives using a set of fuzzy rules to adjust control signals in real time. On the other hand, the Fuzzy-Pid controllers adds an integral term to the mix, which helps to eliminate steady-state errors by accumulating past errors. This makes the Fuzzy-Pid controller more precise, robust, and capable of handling long-term deviations, which is ideal for satellite applications requiring high accuracy. Both controllers combine fuzzy logic with traditional PID and PD methods, but Fuzzy-Pid design offers improved performance, stability, and efficiency, as shown in the simulation results. The systematic design of these controllers ensures stability and robustness in satellite attitude control.
The use of Fuzzy-Pid controllers represents a significant advancement in satellite attitude control systems, addressing the inherent challenges of non-linearity and environmental disturbances. So, unlike traditional PID controllers which rely on fixed proportional, integral, and derivative gains, fuzzy logic introduces adaptability by dynamically tuning these parameters based on the satellite's current state and external conditions. Traditional PID control works well in linear systems with predictable behavior. but space dynamics are highly nonlinear. Fuzzy PID controllers overcome this limitation by using a set of rules that interpret input data, such as error and rate of change of error, to adjust the control effort. This results in improved responsiveness and reduced overshoot, especially when dealing with disturbances like solar radiation pressure and sudden momentum changes. To further enhance performance, the Adaptive Evolutionary Firefly Algorithm, or AEFA, is integrated into the control strategy. AEFA optimizes the fuzzy PID parameters by mimicking the behavior of fireflies, using their flashing patterns to find optimal solutions in complex search spaces. This ensures that the control system achieves the best possible balance between stability and responsiveness, even as the satellite encounters varying conditions in orbit. The comparison between traditional PID, Fuzzy PID, and AEFA optimized Fuzzy PID highlights a dramatic improvement in system performance. Traditional PID struggles with non-linearity, leading to a slower response time and a higher energy consumption. Fuzzy PID improves adaptability but may require significant tuning effort. With AEFA optimization, the system achieves faster settling times, lower steady-state errors, and increased energy efficiency, making it ideal for long-term satellite missions. This advanced control strategy not only ensures precise attitude control but also maximizes the operational lifespan of the satellite by minimizing actuator wear and energy usage. The combination of fuzzy logic and AEFA optimization represents a leap forward in engineering intelligent, robust systems for modern nanosatellite platforms.
To wrap things up, the use of fuzzy PID controllers in satellite attitude control represents a promising advancement in aerospace engineering. The research indicates that fuzzy PID controllers offer superior accuracy and effectiveness compared to fuzzy PD controllers, especially in managing complex space environments. As space missions become more sophisticated, the need for robust and adaptive control system grows. Future research will focus on integrating machine learning and deep learning with fuzzy PID controllers. This combination will allow the system to adapt to unpredictable space conditions such as turbulence or ambient emission changes. By incorporating adaptive and self-tuning mechanisms, fuzzy PID controller could continuously optimize their parameters in real time. Techniques like genetic algorithms or particle swarm optimization could be used to fine-tune the controller settings, ensuring optimal performance as environmental conditions evolve. This research opens the door for more efficient and adaptive satellite control systems, which are essential for challenges of future space exploration. So, thank you.